A bar of 20 mm diameter subjected to a pull of 50 kilonewton. The measured extension on gauge length of 250 millimeter is 0.12 millimeter and change in diameter is 0.00375 millimeter. Calculate Young's modulus, Poisson's ratio, and bulk modulus. So the given data length 250 millimeter, diameter 20 millimeter, and the load is 50,000 Newton, and delta L is 0.12 millimeter, and change in diameter is 0.00375 millimeter. So we have to find out the Young's modulus, Poisson's ratio, and bulk modulus. So delta L is equal to PL by AE. Delta L is available, P is available, A is available, L is available. A is pi by 4 d square. You can find the Young's modulus 0.33 into 10 power 6 Newton per mm square. Now Poisson's ratio, lateral strain divided by linear strain, that is delta D by D divided by delta L by L. So delta D, D, delta L, L is available so that you can get Poisson's ratio to be 0.39. And bulk modulus, relationship between bulk modulus and Young's modulus, K is equal to E divided by 3 into 1 minus 2 by M, that is 2 into 1 by M, where 1 by M is the Poisson's ratio. E Young's modulus we have obtained already. Substitute here the values, you will get the bulk modulus to be 0.5 into 10 power 6 Newton per millimeter square. Next problem. A bar 30 mm in diameter was subjected to tensile load of 54 kilonewton and the measured extension on 300 millimeter gauge length was 0.112 millimeter and change in diameter was 0.00366 millimeter. Calculate Poisson's ratio and values of three moduli. So three moduli is nothing but Young's modulus, bulk modulus, shear modulus. ECK we have to find. Okay, so these are the given data. So Poisson's ratio is equal to lateral strain divided by linear strain. Okay, delta D, delta L, L and D are given in the problem. So you can find Poisson's ratio 0.326 and delta L is equal to PL by AE. From this you can find out the Young's modulus, which is coming out to be 0.2046 into 10 power 6 Newton per millimeter square, and shear modulus or rigid modulus or modulus of rigidity C is equal to E divided by 2 into 1 plus 1 by M, which is coming out to be 0.7714 into 10 power 5 Newton per millimeter square. Okay. Bulk modulus is equal to K is equal to E divided by 3 into 1 minus 2 by M. So substitute the value of E and Young's modulus 1 by M, sorry, Poisson's ratio 1 by M. You get bulk modulus is 0.1959 into 10 power 6 Newton per mm square. So next problem, the bar shown in figure is subjected to a tensile load of 160 kilonewton if the stress in the middle portion is limited to 150 Newton per mm square, determine the diameter of the middle portion. Find also the change in length of the middle, or sorry, find also the length of the middle portion if the total extension or elongation of the bar is to be 0.2 millimeter. Young's modulus is 2.1 into 10 power 5 Newton per mm square. Okay, so let L2 be the length for the middle portion. Okay, sigma 2 is the stress for the middle portion, 150 Newton per mm square given in the problem, and the stress in middle portion sigma 2 is equal to load by A2. P by A2 is nothing but pi by 4 D2 square. P is given 160 kilonewton. Sigma 2 is 150 Newton per mm square. You can find D2 from this, that is the diameter for the middle portion, 36.85 millimeter. And DL is equal to PL by AE. So usually we used to write DL by PA, that is summation of delta 1 plus delta 2 plus delta 3. So in this case, this is L2 we are taking, this is L2, and this length we do not know whether it is equal or different, it is not given, but the area is same, 6 centimeter dia, 6 centimeter dia. So what I have taken is, this is L2, sum of these two lengths as L1, that is this plus this is equal to L1. So that's why I've written here. Okay, P is the load common, it is made up of same material. So this L1, this is the L1 divided by A1, pi by 4, 60 square, right? Plus this is the L2 by A2 of this, pi by 4, D2 square. So this L1, so this can be written in terms of L2, that is 400 millimeter minus L2 will be this, okay, plus L2 by A2. So A1 is nothing but pi by 4, 60 square. Okay, so just substitute the value of P, DL and Young's modulus and substitute D2 here. If you just simplify this, you'll get L2 to be 206.69 millimeter. Next problem, a steel rod of 3 centimeter diameter and 5 meter long is connected to two grips and the rod is maintained at a temperature of 95 degrees Celsius. Determine the stress and pull means force, okay, exerted when the temperature falls to 30 degrees Celsius. If question number one, the ends do not yield, and question number two, the ends yield by 0.12 centimeter, that is 1.2 millimeter, take Young's modulus 2 into 10 power 5 meganewton per meter square or 2 into 10 power 5 newton per millimeter square. Okay, and alpha, coefficient of linear expansion, alpha is nothing but 12 into 10 power minus 6 per degree Celsius. And these are the given datas. Okay, alpha E, T is nothing but 95 minus 30. Okay, T is the temperature rise, so 95 minus 30 difference. Okay, 65 degrees Celsius. Length is 5000 millimeter, diameter is 30 millimeter. And first question, ends do not yield. Okay, elongation alpha TL. Okay, alpha is given, T is 65 degrees Celsius, length is given, you get 3.9 millimeter. Strain is alpha T, thermal strain. Alpha is available, T is available, just multiply it, you will get 7.8 into 10 power minus 4. Thermal stress alpha TE, that is a strain into Young's modulus. Okay, 156 Newton per millimeter square. Pull or force exerted, stress into area, alpha TE into A, that is 156 into pi by 4, 30 square. You'll get 110269.9 Newton. When you look into the second condition, excuse me, the ends yield by 0.12 centimeter, that is delta is equal to 1.2 millimeter. When you consider the yield, alpha TL minus delta would be the actual expansion or actual elongation, whatever it is. So alpha TL already we have calculated 3.9. So 3.9 minus 1.2 will be 2.7. So strain is nothing but alpha TL minus delta divided by L, that is delta L by L. So you get 5.4 into 10 power minus 4. So stress is nothing but this strain into Young's modulus. You get 108 Newton per mm square. Pull or force exerted is nothing but this stress into area pi by 4, 30 square, which is nothing but 76340.7 Newton. Next problem. A steel tube of 30 mm external diameter and 20 mm internal diameter encloses a copper rod of 15 millimeter diameter to which it is rigidly joined at each end. If at a temperature of 10 degrees Celsius there is no longitudinal stress, calculate the stress in the rod and tube when the temperature is raised to 200 degrees Celsius. Take Young's modulus for steel and copper as 2.1 into 10 power 5 Newton per mm square and 1 into 10 power 5 Newton per mm square respectively. The value of alpha, that is the coefficient of linear expansion for steel and copper, is given as 11 into 10 power minus 6 per degree Celsius and 18 into 10 power minus 6 per degree Celsius. So for steel tube, the details outer dia 30 mm, inner dia 20 mm, and alpha is 11 into 10 power minus 6 per degree Celsius, and Young's modulus for steel is 2.1 into 10 power 5 Newton per mm square. And copper rod dia is 15 millimeter and alpha C 18 into 10 power minus 6 per degree Celsius, and Young's modulus for copper 1 into 10 power 5 Newton per millimeter square. So temperature difference, so the temperature rise is 200 minus 10, which is nothing but 190 degrees Celsius. So we know that whenever you go for thermal stresses in composite bar, we need to remember this. That is, compression in one material will be equal to the tension in another material. Okay. So copper is having more value of alpha when compared to steel. So copper will be subjected to compression and steel will be subjected to tension. So sigma force compressive load is nothing but compressive stress into the area. Tensile load is nothing but tensile stress into area. So sigma C AC is equal to sigma S AS. Okay. Sigma C into area of the copper is pi by 415 square is equal to sigma S into area of the steel tube is pi by 430 square minus 20 square. If you just simplify this, you will get sigma C is equal to 2.22 sigma S. And we know that alpha S T plus sigma S by ES is equal to alpha C T minus sigma C by EC, another relation for thermal stresses in composite bars. Okay. So plus goes for steel and minus goes for copper because copper is having more value of alpha when compared to steel. So copper will be subjected to compression. So it takes minus, the other one takes plus. So compression here for copper and tensile for steel. So alpha ST is available, numerical value ES is available, alpha CT is available, EC is also available. Substitute it and substitute sigma C in terms of sigma S in this expression. So 2.22 into sigma S. On rearranging it, okay, so take the alpha values to the right hand side and take the sigma S to the left hand side, rearranging and taking LCM. After simplification, we get the stress induced in steel is 49.32 Newton per mm square, and in copper, just multiply by 2.22, you will get stress induced in copper is 109.51 Newton per millimeter square. Thank you.